Alright, welcome back to Geology 1030 Lab. This week we are studying metamorphic rocks. And to jump right into it, we will get to what is a metamorphic rock. So metamorphic rocks form when pre-existing rocks or the parent rock is exposed to significant heat, pressure, or hydrothermal fluids, which results in fundamentally changing the texture and composition of the rock. Such interactions occur in a variety of environments, including various tectonic plate boundaries or beneath Earth's surface. So two of these locations are considered regional or contact metamorphism. Regional metamorphism occurs where you have plate boundaries. As plate boundaries run into each other, they create high pressure, and this high pressure can alter the parent rock in the process of metamorphism. Or in contact metamorphism, if a parent rock comes in contact with very hot magma, so very high temperatures, it can alter the rock through the process of metamorphism. So can the amount of metamorphism vary? Yes, it can. The amount of change of the parent rock is known as the metamorphic grade, and the metamorphic grade is impacted by the change in temperatures or pressure. So with low temperatures and low pressures, the parent rock will not experience much change and be low metamorphism. But if you have higher temperatures and pressures, the parent rock can be altered to a low, intermediate, or high grade metamorphic rock. So as you increase temperature or increase pressure, it will change the amount of metamorphism or the metamorphic grade. But what impacts the composition of the metamorphic rocks? Composition of the parent rock plays a large role in determining what new minerals will form within the metamorphism process. Minerals in the parent rock may become unstable due to high temperatures and pressures, and therefore their elemental components are reassembled into new or different minerals. Although it is important to know that the mineral composition may be different, but the overall chemistry of the rock does not greatly change. An example of this is starlight. So starlight is a common metamorphic mineral. And in order to get starlight, the parent rock must contain aluminum, iron, and silica dioxide. If the parent rock lacks aluminum or iron, starlight will not form because the necessary elements are not present. Or an easier way to think about this is cookie dough ice cream. If you have melted cookie dough ice cream and refreeze it, it must have cookie dough, chocolate chips, vanilla, and vanilla ice cream. If it does not have the cookie dough, chocolate chips, or vanilla ice cream, then it will not be truly cookie dough ice cream. So how will we identify our metamorphic rocks today? We're going to be breaking our metamorphic rocks up into two broad categories, foliated versus non-foliated. So foliated metamorphic rocks are rocks that have their minerals or crystals arranged in foliations or sheet-like structures. Thus, these rocks have a layered appearance. And our non-foliated metamorphic rocks are rocks that lack the layered structure or foliated rocks, and instead have a more massive or crystalline appearance. So the images at the bottom, you can see the foliated rock have these distinct layers in the rock, and the non-foliated rocks has no layers and it looks very massive. So first, taking a look at our foliated textures. Remember, texture is the size, shape, and arrangement of the minerals. So our foliated texture of slaty. This includes minerals arranged in well-defined sheets that break along very flat, smooth planes. And the grain size of these slaty minerals are very small, which means we cannot see them without magnification. And slaty metamorphic rocks are used to manufacture items that need to be very flat and smooth, like pool tables and blackboards. If you take a look at the slaty metamorphic rocks in the images, you can see these distinct layers, but they are very fine-grained. We'd need to use a microscope in order to see the grains themselves. Next foliated texture is phylitic. These are minerals that are typically fine-grained, however, the foliation tends to be somewhat wavy or wrinkled. In some specimens, a few fine grains are large enough to be seen without magnification, and they appear as just small dots. Metamorphic rocks have a satin or metallic appearance, but note that this satin or metallic appearance is not only in pholitic and can be seen in other textures. So the images below, you can see that they are very fine grained and the foliations are somewhat wavy, as well as the metallic appearance in the image on the left, but the image on the right lacks the metallic appearance. Next, we'll take a look at schistose. These are relatively large grain size, so many of the mineral grains and crystals are visible without magnification. And schistose, sometimes described as having a scaly or glittery appearance. The large mineral grains can somewhat obscure the foliation, so at first you may mistake schistose for a non-foliated rock. And schistose can form from a wide variety of parent rocks, so their mineralogical composition can vary greatly, which also makes them difficult to identify. Make sure that within your rock box you examine the various specimens of schistose rocks. You can see in the images below that these large grain size is causing the foliation to be difficult to view, but you can see the glittery appearance. The final foliated texture we will take a look at is gneissic. Gneissic is a high-grade metamorphic rock in which the felsic and mafic minerals segregate into bands. This produces a pattern of alternating light and dark colored layers, making the texture easy to identify. The grain size is typically large enough to see without magnification, and in the images below, you can see these waves of dark and light colored minerals. Now we'll take a look at non-foliated texture. Our first non-foliated texture is crystalline, and the crystalline metamorphic rocks contain medium to large grained crystals that are roughly equal in size and that interlock. And this could be analogous to some plutonic igneous rocks. And the common crystalline metamorphic rock is marble, which is the bottom left image within the slide. Next is the microcrystalline metamorphic rock. These crystals are interlocked just like the crystalline texture, but the grain size is much smaller, so you cannot identify the crystals without a microscope. And an example of this is hornsfell, which is our second image on the slide. Next is the sandy, non-foliated metamorphic rock. This is like sandstones, and they appear to be comprised of sand-sized grains. Therefore, the parent rock is often a sandstone, and the grains lack the interlocking arrangement. The common metamorphic sandy non-foliated texture is quartzite, which is the third image in the slide. And then finally, the last non-foliated texture is glassy. Glassy is similar to the igneous glassy texture, so there is no discernible grains or crystals present. And the rock has a highly reflective appearance. And an example of this is anthracite, which is the final image on the slide. And next, looking at other non-foliated textures. Some low-grade metamorphic rocks retain identifiable features of the parent rock. At the introductory level, their texture may be described in igneous or sedimentary terms. So an example of this is metaconglomerate. Conglomerate rocks is a sedimentary rock, but if it experiences metamorphism, we call it metaconglomerate. And metaconglomerates originate from low-grade metamorphism of sedimentary conglomerates or volcanic breccia. So its texture may be described as poorly sorted or being gravelly or pebbly in appearance. So in the image, you can see the left is a sedimentary conglomerate, and if it goes through metamorphism, you can still see the difference between the pebbles and the fine-grained matrix, but it is now in this foliated texture. So therefore, we consider this as a meta-conglomerate. And now taking a look at the lab questions. In part 1, you'll just be identifying the minerals, and be sure to use correct spelling when doing this, and also be aware that you have 2 attempts. So if you get any questions wrong in your first attempt, you may go back through and try again. And within this part 1, make sure that you're using the Metamorphic Rock Identification Guide located on Canvas. Now taking a look at part 2. Part 2 is short answer. And a few helpful hints for part 2. First, you will have to identify hornsville and amphibolites and understand the difference between these two. It is important that you'll look at the texture, color, and appearance, and make sure that you're specific in your answer about the differences between the texture, the color, and the appearance. Next, you'll have to discern the difference between marble and quartzite. And a helpful hint for doing this is to try to understand what minerals make up marble and what minerals make up quartzite. And if you buy a countertop and you want to buy a countertop that is marble or quartzite, you may use a testing kit in the store. A testing kit which would include acid and a Mohs hardness test tool. So use this hint to help you answer the question to discern between marble and quartzite. Next, you'll have to understand what bituminous coal and anthracite coal and understand their differences. So you have to remember that these two can sometimes be considered sedimentary and sometimes be considered as metamorphic. And you'll have to try to understand why you personally would decide if they're sedimentary or they're metamorphic. And remember that coal is derived from organic material, which is why it's considered as sedimentary, but also it is derived from an increase in heat and pressure on that organic material. And an increase in heat and pressure is what causes metamorphic rocks. So discern the difference between bituminous coal and anthracite coal and take into account how it is derived from organic material, but also derived due to an increase in heat and pressure. And if you take a look at the image on the bottom, you can see how coal varies with depth below ground. So an increasing depth comes with an increase in heat and pressure, which is the driving force of metamorphic rocks. And anthracite is found below bituminous coal. So the different grades of coal have to do with the different depths they are found below ground, which impacts the heat and pressure of those coal layers. And then finally, you have to understand why metamorphic samples vary. And to do this, you must take into account how long and intense the grade of metamorphism is on the different metamorphic rocks. Good luck with this lab. Please, if you have any questions, feel free to email me, and also stop into your lab time that is designated on Canvas. Good luck. Please let me know if you have any questions.